Hey, Ghislaine, how are you? We'll start in about a minute. Just give a chance.
I am
Busy working?
I'm trying to I'm working on NCL questions
Oh, I see.
now.
So pretty busy, huh?
I'm so close. Like I think I'm above 83% completed.
Okay.
I'm trying to find one answer in a Wireshark package, and like I found everything. It's like somehow I'm trying to find the receipt to a purchase, and I have everything except for the address of where everything is being sent.
So did you find which packet that was coming from or no?
No, like I keep finding things adjacent to it or related, and either they're missing information or they have some informations that I did need. And like the one thing that so it's a ticket purchase, and the only thing that's actually left is just like where the tickets are being sent to.
I see. Have you tried filtering? I'm sure you did.
I'm not even sure what to filter. Actually, the way I think the way that I'm doing it, I only group them by like HTML, potential HTML pages,
Mm-hmm.
and then I'm looking at the URL and seeing like which one sounds like it's related to what I'm looking for.
Maybe look at protocols. Filter by protocol. So those type of purchases, well, you know, HTTP, HTTPS, you can screen down on those and then looking at the type of services that goes. So look at the protocol. That's probably what would probably be better than just looking at file types and things like that. It might not be HTML, it might be text or something or another format.
Okay.
Yeah, that's
Well,
where I would start. There are other tools that does forensic a little bit better than Wireshark, but yeah, I think I did use one for my CIS27A.
Which tool is that? That's better than Wireshark.
For forensic, yes,
Yes.
there are better tools than Wireshark. Wireshark is just good for monitoring.
But
There.
which tool is that? If you don't mind mentioning the tool that's better than Wireshark.
Give me 1 second, I'll show you. Oh, maybe I don't have it on this. Is this Michelle? I see 2 on my thing.
Oh, sorry. Let me change it.
Okay, that's okay. Yeah, I can send you the information. But I did do a video for 27A on how to use a forensic tool for that. It actually is better looking at the packets if you want to dig in a little bit deeper. But I can give you the information. I don't have it on this computer, so I moved some stuff around, but I can pull it up.
I'm just
Actually,
curious. I'm not competing in NCL. I'm just curious what that is.
okay, give me 1 second. We'll
really?
start shortly.
All right. Sorry for interrupting. But Michelle was competing.
No, I'm not. I just want to know what tool is better because I'm curious what tool could be better than Wireshark.
Well, Wireshark is really good at live monitoring, so that is more on defensive and reactive approach. And then if you are going back and you're doing like you really want to dig for forensic, hold on, then you can use.
I did the CrowdStrike forensic thing just for fun.
Oh, how did you do?
All I can say is top 50% because they didn't really release the scores. I could only see the histogram of where people placed.
Well, hopefully they would consider, because I know a lot of people scout using that. So this is the tool that I would recommend if you want to do more forensic after you already have the PCAP file. And it's supported, it's cross-platform, so you can use it on Windows or Mac or Linux. And it's really good at extracting those. Something to consider. I actually wrote a lab for it for 27. I don't know if the new faculty is going to use it. I did share my whole shell with him, so maybe he'll be able to use it, or he might use practice lab or something like that. But okay, so if you didn't catch that, it's called Network Miner, and it is free download. They do have like the paid version. You don't need the professional version because the free version actually is adequate. They have a tutorial and videos on how to use it. Okay. It does similar things to Wireshark, but it is designed for like forensic. And you know, the people who wrote this, they were really doing some investigation with like vector attacks and stuff like that. So and I know some of the training stuff is like outdated, but you can look at like cap loader and packet cache, polar proxy. There are like specific areas that certain part of the tools can do. They're like, so the whole deal is if you get the professional, it comes as a suite. But if you can actually get like individual tool that you can use. Yeah, Wireshark is good for like network monitoring and live monitoring, but if there are certain tools in forensic that's a little better. Okay. Anyway, all right, let's switch gear and let me go back to my RCCD. So I just want to remind you that I am not going to hold live session on Wednesday. I'm going to have a video recording up. I have a program advisory meeting, which I'm required to present some stuff for curriculum. That's going to run a little bit over 5, like until 5:30, and I don't want you to wait. So in this week, we are going to skip chapter 8, which is a review of 6 and 7. We're going to go into 9, which is on Amdahl's law. What I did was I pulled some stuff on LinkedIn Learning that's really good. I watched several of their videos to see how good they are. And a couple developers, they put together some tutorial videos, and I put the link for that here. If you have not signed up for LinkedIn Learning, you would use this link. I create a link for you to be added, and then it will just authenticate through your portal, meaning that you just log in using your RCCD email account, and then it's going to bring you to the advanced Python with Amdahl's law. So they do a whole section on parallel and concurrency processing, and how to really build out the programming, doing some tutorial and challenges, and they explain the code and they do it well. So if you have time, please watch the video. I think it's going to give you a lot of understanding outside of the textbook resources and our notes and, you know, my video and the lecture. So that will be useful. So I will add the lab video along with today's lecture recording here. So just go ahead and watch the lab video. We are going to do 2 exercises. One to just expand on the sort algorithm, and then the second one we're going to do something fun. So I will put together the video for you to be able to use, and it's best that you do these parallel processing with using Linux. So if you don't have your Linux virtual machine, please let me know. I can put up a plain Ubuntu one with a larger storage, but you will have to take time to download. If you can create your own, do not put the desktop on there, and make sure that you have about 20-25 gigs of virtual hard drive. Otherwise, you're going to run into issues when you're installing packages. Okay. So today we're going to cover Amdahl's law. This is in computer science and computer engineering. This is a topic that's going to be discussed, and it's usually coming up when the lecture is about parallel processing or parallelizing your program using multiple processor. And so last chapter we started looking at parallel programming and how to really look at resources to be able to allocate toward your program and compare that to the sequential program. This week, we're going to take a look at how many processors and the type of resources that we would dedicate to our parallel program. What's going to be the enough amount? How is that going to work? How are we going to be able to compare? And so on. So So we have to really find a way to parallelize our program. And we know that we can't parallel 100% of our program. There will be certain tasks in your program that needs to be sequential. And so about the maximum that you can parallelize your program is about 95%. And so that's ideal, right? Like that's the most that you can do. Some program is actually less, 20%, 40%, or even 10%. And so it really depends on how we design our program. So if we parallelize our program, how many processors can we dedicate to the parallel process? If you have 8 cores, it does not mean that you have to dedicate all 8 cores to the parallel program portion of your application, but you can actually dedicate 2 or 4 or a certain amount to really execute the task that you need to accomplish. Okay. So here it talks about finding the balance and using Amdahl's law to really give us an estimate based on our solution. If you design your program and you wanted to see, is it efficient? Is it effective? What kind of speed up do you have? Is the resource that you're allocating to your program appropriate? Then we can take a look at how we would use Amdahl's law for that. So Gene Amdahl was a physicist. He was curious about how to really use computing or computation to calculate more advanced mathematical equations. So he wanted to really measure out the amount of data that the computer will process using parallel processing. And so that's how he dabbled into the computational area. And he wrote quite a few books relating this topic, and also data processing and how to really use data structure. So you will be able to find his books out there. So in concurrency and parallelism, we know that it is a powerful tool. Compare that to sequential, we can maximize the capability of our modern processor with the architecture that we can allocate the number of cores to execute the task, where we would break it down to certain subtasks, and we can either apply concurrency, or we can implement where all the tasks can be executed by all the allocated cores at once. So it's important for us to really look at what is going to be our limit in the speed, because just like everything that exists, there's always a limitation. And when we improve with concurrency and parallelism in the program, the law doesn't always allow us to increase the speed, and it's not always going to be a direct relationship. You will plateau after a certain number of cores. So the way that we would look at Amdahl's law, in that we would use it to really predict, and it will not give you the exact speed up. In some sense, it will give you an estimate, okay? Because we don't factor in the memory usage and other areas that would be considered to really measure to be exact, but we will have a ballpark of what that would be like if we implement certain number of core for the type of task that we're doing in the application. So the example here, it says that if you need 20 hours to complete one single thread, let's say that that's what the computer would take to be able to execute it sequentially. But 1 hour portion of the program cannot be parallelized. So the remaining 19, which is 95%, that can be parallelized. So we always assume that we know that there's not 100%. of your program that can be parallelized, but there will be about 5% that's going to be sequential. Okay. And regardless of how many threads that you can really dedicate to the parallelized execution, the minimum execution time cannot be less than 1 hour, that 5%. Okay. So our limit would be that it's going to be 1 over 1 minus p, which is going to be 20. So we know that it takes 20 hours to really run that program. 1 hour of that 20 hours is going to be sequential, and the other 19 can be parallelized. Okay. So in that, what we would denote is we would have speed, which is going to be the time that it's going to take to execute our program in full. And in our example case, that will be 20 hours. And that can be measured in a certain amount of time. That could be seconds, that could be hours. And so in the example, it says it's 20 hours. The speed up is the time that measures the benefit of executing computational in the parallel. So that is going to be the measurement that we can use with parallel. And the time that it takes for the program to execute serial, that will be 1 processor, divided by the time that it's going to take for us to use the parallel, which is multiple processor. So your latency would be T over 1 divided by T over J, where J is going to be the time that it would take to use multiple processor, and J would represent the number of processors. Okay. Now, if we started to implement a pool of workers, and we talked about this about 2 weeks ago, or last week, where we would have each worker work on a certain task or a certain job. And so that way it will be fully parallel. So in that, you would bring in multiprocessing module in Python, and then you will create, your worker pool, and then be able to have each of the worker work on the task. Then the job would be equally divided into the n sections. And then the worker will work together. So therefore it would take 1 over n of the time that it would take 1 worker to complete. So if you tell me to do a certain chore, right? Like organize my closet. And if I'm doing it by myself, let's say that it's going to take me 10 hours. But if there are 10 other people to help me, right, we would then equally divide that up. So each of us will work concurrently with one another across 10 people. And so that we can tackle the task at a much faster time. And that's what we talked about last week. So in this case, when you look at that, that will be 1 over n of the time that it would take for the 1 worker to complete the job. So in my case, it takes me by myself 10 hours to do a task. And if there are 10 people total to be able to work on that task, that will be 1 over 10. So that will be fraction of the time that would be, right? But in the entire program, keep in mind that we cannot take the entire program and make it parallel, okay? So now in the text, it gives you this, where it gives you the breakdown, okay? So before we go into this formula, let's answer the questions. Based on Amdahl's law, what is the program speed and speed up? So the speed would define that it is the time that it takes the program to execute in full. This can be measured in the increment of time. Okay, like seconds, hour, microseconds. The speed up is the time that measures the benefit of executing a computation in parallel. So we're only going to look at, right, the result from executing in parallel. And the time that it takes for the program to execute serial divided by the time that it takes to execute the parallel, like what we talked about. If it takes a person 1 hour to do that task, right? But if you have multiple people, that will be 1/n. So it becomes a ratio of the sequential execution time to the parallel execution time, like what we talked about, 1/n. So any question with this? So keep in mind that when we calculate, right, the value for speed up, okay, it is just the outcome. It's a way that we can measure how that program would be in executing parallel. So to really look at the program efficiency for number 2, it asks you, what does the program efficiency speed up divided by the number of the parallel processor calculation provide? It really tells you how well the parallel processing resources are being utilized, right? Focusing on the benefit. Okay. So what it does, it tells us how well the parallel processing resources are being used. So in this assignment, we mainly focus on the concept, right? And then we would work on the lab with the programming. Any question with this? And I took this from the notes. And then we just reinterpreting this from this. Okay. Okay. So before we calculate the estimated speed up for our program in number 3, let's take a look at the breakdown of your Amdahl's law. So the equation that the book gives you for the most part is this, okay? In the example that T1 represents the time that it takes to sequentially execute. So we know that our program would have 2 parts. One, it's going to be sequential. The other would be parallel. You cannot have a completely 100% parallel program. So therefore, you would have a B times T of 1, which is the time that it takes to execute the sequential part of our program, which is this first part right here. And then the second part would be representing the sequential on the bottom. Okay. And we know that when we measure speed up, we want to look at the ratio, right, that it would take to be executing in the parallel using multiple processors. So if we simplify this, we would have 1 over B plus 1 minus B over J. Okay. And so in the case where if we have 40% of our program is parallelized, that means that we would have 60% that would be sequential. Then, and we would allocate 4 processors for the parallel parts of our program. That's going to make it 4 times. Okay. Then when we plug it into the equation, we first need to determine what is going to be the difference, right? The sequential. That will be 60%. So here you have 0.6. Okay. That will represent your B. As I calculate that out here. Then we would have 1 minus 0.06, which is the 40%, divided by 4, because there are 4 processors, right? Your J is 4. So you can plug this into your scientific calculator, and you would get approximately, rounded off, would be 1.43 or 10/7. Okay. So what do I need to really start the calculation is that I need to know what would be the percentage of my program that will be parallel. So how can I really determine that, right? So when you write your program, look at in the LinkedIn tutorial, they talk about how you can either look at the data to really implement the parallel, or you can look at the functions. But the approach that we've been using for our lab in the last couple of weeks is to implement it with the functions, not the data. When you work with data container like dictionary and so on, or a list or an array, then you can start looking at the amount of data that you want to parallelize. So for example, if you have a very large array, right, let's say 1,000 elements in it, and you can break that into half to make it parallelized, and then the other 50 would be sequential, let's say, okay? But the approach that we've been using in the last couple of weeks, we just simply implement it with functions. So if I have, let's say, 10 functions, just to make it easy for the example, right? 40% of my program is parallelized. That means that we would look at 4 of the functions that would be parallelized. And then the other 6 functions are just sequential. All right. So that's how we're able to get down to the percentage that will be parallel. And then you also need the value for the processors that you would use for the parallel parts. And you are not required to dedicate 100% of your multiple cores to this particular program, right? So if we, like I mentioned, if we have 8 core, we can give it 4 core. And in some case, you can also increase the core as you go for subsequent functions by implementing that through the code. All right, so let's practice the calculation for number 3. If the computer program is 70% parallelized using an 8-core processor, use Amdahl's law to determine the estimate speedup of the program. So we need to first determine the B, or the sequential part of the program. We know that it is 70% parallelized, so you would take 1 minus 70%, which gives you 30%, or 0.3 is sequential. Then we would plug it into the equation. So we would have 1 divided by I'm sorry, this is 0.3. So I'm off right here. I just caught that. Okay. Let's fix that. I had it reversed. Okay. So we would have 1 over B, which is 0.3. We achieved that. Plus 1 minus B, which is 1 minus 0.3 divided by 8. So let's bring up calculator real quick. So I have 1 divided by, let's start that, 1 divided by 0.3 plus 0.7 divided by 8. Yep. So we should be at 2.6 or 2.58. Okay. Any question? So once you have your B, you can simply plug it into the equation along with your J, which is your number of cores, right? And then your, yeah, that's all you need actually. So just the percentage for parallel to be able to determine B, which is your sequential, then you can use that in the equation. Any question? And if you wanted to use this format, you can simply copy and paste the equation over, or you can do insert equation, you can type it out. So this speed up value would tell us, right, by putting in 8 core to parallelize our program at 70%, right? It's gonna improve the program that much. Now, if you put in, let's say, you know, there is some direct relationship for a certain number of core to the improvement of performance. However, right, you will reach a total number of processors that will actually reduce the performance or plateau out. It's going to even off or even lower the performance. So based on this, right, it talks about how much speed can you actually gain. There is an upper boundary, which is going to be the sequential part of your program. That's going to set the sequential nature of the overhead sets the upper boundary. Okay. You have a limit in that even though your core can be infinite, your sequential performance is going to be the limit of your program. So here we see that there's proof. It suggests that you can gain by putting in more processors. And as the processor increases, the speed of the execution of the whole task increases. However, it does not mean that it's continuous forever like that, right? There is a maximum limit in that it will not improve any more performance, even if we put in more processor. And so therefore, as we add more processor to a concurrent program, we would then at one point reach the limitation and get less improvement for the execution time. So in the next question, for number 4, it asks you, when implementing the concurrent parallel techniques, what is the upper boundary on how much speed up of the program will gain? So your upper boundary is going to be your sequential part. So the sequential nature of the overhead portion required in the program always set the upper boundary and how much speed up the program will gain. As we know that the program will never be without sequential. And that would also reference number 5. And number 5 asks you, what is provided in using Amdahl's law calculation of the overall speed up that parallelizing a program, the program upper limit? Any question? So when we think about this, we would look at the relationship between the cores and the percentage that we parallelize our program. And there is a useful chart that is included in your notes, but you can find it everywhere on the internet. Okay. Let's look at that, this chart. You can increase the size to make it larger. So if we look at the color coding here, the green shows that this is at 95%. And so as you see that there's a direct relationship with the number of cores until it gets to here, which is 2048, about 2000 processor. So for a highly parallelized program, so if we parallelize our program at 95%, we can keep increasing the core until we get to about 2000 core, and it's going to either plateau out or it's going to drop. Okay. Now in the 75% parallelized right here, right? It actually is lower in the number of processors that we can implement. And then even go lower for the 50%. So if we do 50% parallelize in our program, it does not make a difference between about 1620 cores to 128 cores. So it pretty much is stable after that. Okay, compared to the 75%, when you go 75%, about 100 cores or so is going to give you about the same as 1000 core. So as you can see that in the program, when you design your program, if your program is highly parallelized, then you're able to capitalize on the number of cores until that certain limit, because you do have the upper bound. Any question? So using this chart, what we can do is we can answer number 6. Based on Amdahl's law, how many cores can be implemented for the program that is 95% parallelized and 50% parallelized? So a program that is 95% parallelized can have up to 2048 cores to achieve the approximate speedup of 20. More cores will be the same or slower. So going back to this chart, if you can see we max at 20 speedup, right? At about 2048. And then anything beyond that, it's going to either be the same or lower. Now for 50%, ballpark, it's going to be about here, 16 to 32. So about 20 cores where you're going to have pretty much the same after that for 2 speedup. Okay. So a program that is 50% parallelized can only use up to 16 to 32 cores to achieve the approximate speedup of 2. More cores will be the same or slower. So in the consumer PC, right, we can have something in the scale of this right here, right? Like I've seen people with systems that have 12 cores or higher a little bit. But in the consumer PC, you don't see this many cores, thousands of cores, right? Now, going back to the last chapter, it talks about how does that translate to GPU, because GPU actually is thousands of cores at work, but it is slower than your regular processor. So in the case where you're using thousands of cores, right, depending on how parallelized, the percentage of the parallelized program that you design. Now, we don't always have to parallelize the program, right? We have to really think about the goal, the objectives of our program, the type of data that we have, the tasks that we need to achieve in that program. Because in some cases, if we parallelize, it might not be beneficial to parallelize. Okay. And the book discussed that in various sections. Any question on 6? And the notes is not very long. The chapter is not very long at all. So if you do have time, please read, and you can also read the prior chapter. It talks about some of the concepts that were covered before reviewing that, and then it goes into concurrency and why would we use concurrency and why would we not use parallel concurrency in certain parts. So it draws attention to Amdahl's law with the relationship to the diminishing returns law, which is an economic law. And it really is applying the Amdahl's law depending on the order of improvement. So here I highlighted some points. If the order of the separate tasks of the program is chosen to be improved in an optimal way, it would decrease the improvement of execution and demonstrate diminishing returns. When you're using an optimal method to apply to those improvements will result in the greatest speed up, leaving those improvement yield smaller speed up for later. Now, if we reverse the sequence in choosing the resources, we can improve less optimal components and more optimal components speed up achieved through improvement, which increase throughout the process. So what does this mean, right? In cases where you improve by parallelizing your functions, and what will happen is more of the complex functions happens closer to the end of your program or in the later part of the program. So in the sequence, it's still going to go through and it's going to be able to execute that. So what they're saying here is that it would be more beneficial to implement improvement in the reverse optimal order. More optimal components usually more complex and take more time to improve. So we can take that and we can put that in here. It says that using the Amdahl's law applied to the law of diminishing return, when you're using optimal method and reverse optimal method, the optimal method indicates that first applying to those improvements that will result the greatest speed up. So you would only parallelize the area of your program that's going to yield the most return. Okay. And then you're going to leave out, or you're going to focus on that first and then transition that to the smaller tasks that will yield less at the speed up. And that's how you're going to truly get, the max out of what it was invested. And then if we are doing the reverse optimal order, as more optimal components are more complex and it takes more time to improve, improvement and speed up can be achieved by adding more processor to the system. So this is why they say that you don't have to dedicate all your processor into every single parallel area of your program. What you can do is you can focus on what's being gained the most as improvement in the speed up, the higher value of the speed up first. And then as you go on the subsequent, on the later, more complex functions, you can increase the processor allocation, and that's how you're going to maximize your resources. Okay. And this is just a way for us to really determine how we would be able to approach our program design, our techniques on how we would solve a certain problem, right? You can solve a problem sequentially, you can solve a problem using parallelism. And you can also implement what would give you the best in return. Okay, for question 8, true or false? Increasing the number of processor with a fixed problem size per processor leverages weak scaling to accomplish more work in less time. That's false, because when you increase the number of processor, right, for that same problem, that's a fixed problem, it doesn't change. Size per processor leverages the weak scaling to accomplish more work in the same amount of time. So when you put in more workers, right, you're able to accomplish more work for that same amount of time. Like what we talked about earlier, it would take me by myself 10 hours to organize the closet. But if there are 10 other people, right, we can accomplish more in that time. Any question? Okay. Question 9, what is the trade-off in achieving the best possible speed up in parallelization? So earlier in the semester, we talked about the trade-off with time and space, right? Memory and time. Now, in this case, what we see is we do see trade-off with processor and increase in time for parallelism. So the answer to this is increase in the number of processor versus the increase in how long is the parallelism. So when you put in more processor, you do have some improvement in, right, accomplishing that task. Okay. However, that's not always the case, right? We talked about that earlier. And then when you implement parallelism with less number of processors, that doesn't really change. So like if you put it in 2 processors compared to 4 processor, you have now less workers. And so that is always a balance. You want to achieve certain balance. Any question? So this is the example program from your textbook. I included it here so that way you can take a look at it. Okay. You can see how that's, it's using process pool. It creates the workers. And then we implemented parallelism there. You can put it into your Linux machine and run it, because if you put it into your interpreter, it's going to give you an error. Yeah, it has to be run with because on Visual Studio, I think that you have to take a look at how you are linking check to see if your packages and things are there. Because if it's not going to be able to output. So put it into your Linux machine and run it. Okay. Yeah, on Visual Studio, if it doesn't run, it will tell you why it doesn't run. It might be that it's not able to, it's not able to see certain object. If that's the case, then it's probably just not able to read the packages. So use it on the Linux side. So for the lab this week, we have to use Linux just to minimize all the extra issues, because I won't be live to help you, right? But if you run into problems, please send me a message. I do have a class at 7:30 or so after that. So I can answer if need be. Okay. All right. So last question, which is really easy for number 10. Since Amdahl's law does not consider the overhead parallelism or speed of memory, why is this law used in programming, right? Remember, it is only an estimate. So what it does is it gives us the idea of where and how much we can further optimize a concurrent system by increasing the available processors. It helps us in effectively identify good theoretical strategies in improving computing speed using concurrency and parallelism. So you would know how much you want to resource you need to dedicate to it for it to improve performance, right? It's not exact, but it's going to give you the ballpark. Okay, so keep in mind that it is an estimate. You cannot use it to really measure the exact performance and compare that, right? Scientifically, you cannot. But you would have an idea, or at least just a ballpark of how it should be. Question. So next week, we're going to try to hit both of the chapter on threads. I will see on how the content would be for your assignments, but that's my objective for next week, is going to do 2 of the thread chapter together, because the pattern section is going to be lengthy. So I know for sure that I'm not going to be able to cover all of the chapters by the end. However, right, we're going to hit all the major area that's going to give us the learning outcome for this course. Yeah, so new processes before concurrent. Yeah, it's not able to fork. You get a runtime error. Because it's going to want to do the sequential, right? It didn't let you. So let me find out. I think there's a fix for it on the VS side. I know that you can, I think that you have to do some configuration with it for the multiprocessing package. I'll give you more details, maybe in email. Okay. Let's see. Yep. So Michelle, I'll check back with you on that. And then I'll share, actually, I'll share with everyone, because some of you might be using VS as well. Okay. All right. So for this chapter, short, sweet, okay, but do check out the tutorial videos on LinkedIn Learning. And once you sign in on LinkedIn Learning, there are great resources on there on Python, on CompTIA certifications, on other certifications, and so on, right? Before I would individually invite people, but it takes time to just get the email, click the email. But so now, like, we're able to do the admin through the link share. So once you click that, you just authenticate and it automatically sets up your account. But if you already have a LinkedIn Learning account that you had previously used, that was free with RCCD, you can you can just use that. Okay. So LinkedIn Learning is formerly lynda.com, right? Microsoft bought it and they took it over and they flourished it. So they have additional tutorial videos on, you know, from jobs to business to technical stuff. Lately, there are a lot of really great technical stuff on there. And so there are some of the areas that, you know, the book talked about it, but if I missed it in the lecture or if you didn't catch it, it might be also good for you to look at the tutorial, and they also explain their code line by line. So it helps. Okay. All right. Any question? Okay. Let me stop recording.